Hello all, welcome back to our channel, and this time I have brought to you another application circuit using operational amplifier. So we have covered a lot of studies so far on our channel. So if you are new to the channel, go back, refer to those videos, very interesting content and technically rich, and subscribe to the channel for getting information and alerts about more such videos. So here, what we see, you have an operational amplifier, and this concept I'm demonstrating you by taking help of a general purpose circuit simulator. You can just download from the internet any circuit simulator. So from the library, I picked up these components. If I right click it, you see there are properties that I have already available. AVOL stands for the open loop gain of an amplifier. We know the operational amplifier has an open loop gain without any feedback. So it is set to be 1 mega. Then there is a gain bandwidth product. GBW. G stands for gain, BW is bandwidth. That's the product is about 10 mega. So it's decent one. And the VOS is the offset voltage of the amplifier, that is 0. So it's ideal situation for the offset. Then there is a second line that says EN. That's the internal voltage source of your operational amplifier. Then you have IM, current source inside the equivalent circuit of an op-amp. Then you have Rin, that is set to be 500 mega, which is a differential input resistance of your operational amplifier. So it's a universal operational amplifier. From the device library, you can just click here and then say there are range of operational amplifiers, so many op amps you to choose from. So I have chosen this. It's a linear single pole op amp with no internal nodes or output voltage range limit. So output voltage can swing to any voltage levels, and there is a single pole op amp, so it has a frequency response of a low pass filter and just a single pole. With that said, okay, I will press escape button from the keypad of my laptop to get rid of this component. And then I have this voltage source, which is providing me a 12-volt DC voltage. And it has two terminals, positive and the negative. And I have connected the positive terminal of this op-amp to the positive supply rail of, I have connected the positive voltage, positive terminal of this voltage source to the positive supply rail of an amplifier. So if there is a connection or not, I can ensure by labeling the net such as V plus, and here also labeling the net such as V plus. And what I can do, I will right click this net and I will click highlight net. So I see there is this connection. This is the question mark coming over there because I have pre-simulated this circuit just to before explaining you through this video. So that's why there is a question mark. I have run some analysis on it. Once that is done, I see that it has a positive terminal and the negative terminal. To the positive terminal, I have a voltage source, or it can be a current source as well. So it's a signal source, I would rather say. And then right clicking it, I see I have set up a DC value of 5 volt and I click OK. Then as you can see, the negative terminal input terminal of op-amp is connected back to this node, which is labeled as V out. And the output of the operational amplifier is coming back to V out. In between, there is a diode though. So diode is connected. So we'll see what the function of this diode and overall the function of this circuit right now. From the output, I am connecting this capacitor, which has a value of 1 micrometer. 1 microfarad, I'm sorry. And then right clicking a diode, I see I have picked up a general purpose diode, and I can choose a new diode also. So I just keep it okay. The negative supply rail of the amplifier is connected to the ground, and hence the circuit is complete. Now let us understand briefly how this circuit will work. So with the input connected to the positive input of the amplifier, and if the input to the positive input of the op amp is greater than the input at the negative terminal of the op amp, assuming the capacitor is initially fully discharged, so the output is not having any voltage levels, and we will say that there is a zero rather. So zero is appearing here. So it is assumed that it is connected to the ground. So with the voltage at the positive, if this voltage is greater than the voltage at the negative, the amplifier output tends to be positive. On the other hand, if the input at the positive of op amp is less than the input of the negative, the amplifier's output tends to be negative. Based on that, your diode can get forward bias or reverse bias, and then the circuit will be perceived or understood in that way. We'll see. So let's say I have a positive voltage applied of 5 volt. Apparently, the voltage at the positive input is greater than voltage at the negative input. Hence, the output tends to be positive, and that output, if it is greater than the forward voltage drop of a diode, it makes the diode forward bias. Then the loop gets complete. This signal comes back to the negative input, and then the circuit is apparently a voltage follower, assuming op amp has open loop gain, which I just showed you in the beginning. It is set to be 1 mega, which is reasonably high. Because of the high gain, both voltages tends to be equal to each other. So the voltage at the positive will come at the negative, which is nothing but voltage as an output. That voltage is going to charge up your capacitor in a certain time given by a time constant RC. The resistor will come from where you need to tell me that where is the resistor time constant will come up here. Okay, so voltage will then try to catch up, or try to catch up the peak of the signal. So if it is DC constant voltage, the voltage at the capacitor will reach to the constant value within a certain time period. Okay, let's assume this voltage then falls below the voltage at the negative input. Then the output here comes negative, which open circuits the diode. Diode is no longer a forward bias, rather it is reverse bias. The loop gets broken because the diode is acting as an open switch, and then the voltage at the capacitor remains to its fully charged level. The capacitor remains charged. Of course, it will find a path to discharge through some component or through some mechanism, but till the time it will hold up the charge across it, because C equal to Q over V. Okay, and then after some time it will start discharging. But in the moment, if you still have the voltage, greater voltage at the positive that goes up more than the voltage at the negative, again the diode will forward bias and the same cycle continues. So why not run a simple operating point analysis first, assuming you have this DC 5 volts, and we'll see what voltages and the currents are there. So that's correct. So before that, let me just drag this voltage here, right here, this net I am dragging up. That sounds pretty okay now. And maybe diode a little bit down. That's okay. So what I'll do, I will run the DC analysis, the DC operating point analysis. So don't pay much attention to this syntax and this syntax because that I had earlier run. I'm using the 12-volt DC to power up the amplifier. So what I'll do, I will just click simulate. I will click edit simulation. Then I will, so many analysis are there. So I will choose DC operating point. It helps me to compute the DC operating point, treating capacitances as open circuit and inductances as short. So the capacitance will be treated as, oh, 1 second. Let me just undo it and I will simulate this one. I have chosen the DC sweep. No, I want DC operating point analysis. So I just have this syntax right here, dot .op. Okay, and then I will click OK. And look, as soon as I choose this DC operating point analysis, let me drag it somewhere right over. I have the other two analysis, that is dot .dc and dot .trans, get disabled because this got enabled. So at a time, you can run only one analysis in Spice. Remember that. Once that is done, I will just click run. And it now plots me. It now prints me all the voltages and the current. So voltage at the node N001, which is this node right here, because that's our 5-volt. And the voltage at the V plus, which is right here, is 12-volt. Then the voltage at the output is 5-volt as expected, because we said that the voltage at the positive input of op-amp is greater than the voltage at the negative input, assuming the capacitor is initially fully discharged. The output voltage is 5-volt. That's correct. So it acts as a voltage follower actually. So it's yeah, now it acts as a voltage follower and it's reaching the peak of your input voltage also, although it is DC. Then voltage at the N002. So remember, when you say V out is 5.0, approximately 5-volt, this is the V out. So voltage at the negative input is also 5-volt, and voltage at the positive input is also 5-volt. But there is little bit doubt here. Why not? We see if the voltage at the negative is 5.001 and the voltage at the positive is 5-volt. So apparently the voltage at the negative is larger than the voltage at the positive. So the output should tend to be negative. So you got to tell me why this is the case and just contradictory what we talked. But before that, before I explain you that, let's go to the current through the capacitor. It is like very small current flowing through the capacitor, 1 micron. And then the current through the diode is about 1.99. That is nano ampere. So it's a very less current actually, because the loop is complete here. So let me just check that. And there is the current from the input voltage source is 2 nanoampere, excuse me. And I of V1, that is your current from the power supply of op-amp. That is again 1.3 into 10 to power minus 8 amps. So let me just take you to the next explanation. So our question is, if I want to have the voltage at the negative and the positive input, if I compare them, the voltage at the negative input tends to be slightly larger, is about 1 millivolt. Yeah, 1 millivolt greater than the voltage at the positive input. So that is probably due to the gain of the amplifier that we have said. Remember, the open loop gain of the amplifier is about, let's check that how much is that gain. So what we'll do, remember this voltage is 5.00199. So we'll right click and we have set the gain of 1 meg. So ideally it is infinite. So why not set to 100 meg, for example? Once that is done, rerun the analysis. And now you see the voltage at the negative input of the op amp is voltage at the positive is equal, approximately equal to the voltage at the positive of the op amp. So you see the voltage here is 5 point here, 5.002 volts, and the voltage at the positive is 5 volts. So increasing the gain of an operation amplifier can help with that. Okay, so that's why you have to make sure that your gain is pretty high. Now the current through the amplifier is 5 atto through the capacitor, that is right here, IC1. The current through the diode is 1.99 or 1, like that. Now the capacitor I have increased to 10 microfarad actually. So how about I want to decrease the value of a capacitor, and now I'll see if there are some changes. Apparently that is 1 micro, and here it is. So the voltage at the output is same, the current through the capacitor is changed, and that's it. But it is acting as a voltage follower, and output voltage is equal to the input voltage. How about now I set -5, for example. If I choose -5, and now I expect that the output voltage, let us first understand what the output voltage would be. So with the -5 volt at the positive input, your output tends to be negative. That will reverse bias the diode, and the capacitor will hold its voltage across it, uh, what it was initially holding, that is our V out, and that voltage is again appearing right here. So let's run and see how it goes. If you see that there is some iteration going on and some stepping going on here, but I don't want to have a stepping. Let me just stop this analysis, and yeah. So now that is again the case, correct? So the spice was actually calculating it, and I stopped it by interrupting the analysis. Let's rerun it. And now you see in the left bottom extreme, you have some computation is going on. The stepping G-min steps, ppm, Newton-Raphson iterations, and I am asked to press escape to quit. So if I let it go like this, it will keep on doing that, but I choose to press escape to quit and to see what results it prints. So it prints me -5 at the input, at the positive, and this is DC power supply for the op amp. And now you see -4.99999. So it's approximately equal to what I have at the positive node, and the capacitor is maintaining its output voltage. So it is uh, now called as the voltage. Yeah, you can still call it as a voltage follower, or uh, the voltage detector, or voltage level detector. You can call it in this way. You won't call it as a voltage follower because the loop is open now. That is reverse bias. Okay, but now here's the current through the diode is still -2.199 into 10 to the power 8. So it's like 21 nanoampere current is flowing. In earlier case, it was like 1 nanoampere, but now 21 nanoampere. How about we just try to see the voltage drop across the diode? right? So in this, so why not label this net? Let's call it, label this net, let's say A, and this is not AB or something, let's say. So we'll have the voltage difference between A and V out. So that is the drop across the diode. So if I run the analysis, and or before that, let me just do one thing. Let's do it for the forward biasing over diode. I use 5 volt here and then run, and I see now this VA is a very high output. V out is 5.002. Why is that the case? So we have to understand that. Let me just do that. Okay, so after running this DC operating point analysis, how about we just sweep the DC voltage in a particular range, and then track the output, and we'll see how the circuit behaves. So what I'll do, I will just click simulate, edit simulation command. I have this DC sweep analysis right here. So I have to actually name the source and then use the type of sweep, start value, stop value, increment, etc. So I have done so many times this analysis. I'm not going to explain you how to input those values, because refer to other videos, earlier videos on our channel. So right here, you see there is already a syntax. So I'm sweeping a DC source named as Vin, which is this source. It is stepped from 0 to 5 volt at the increment of 1 volt. So I will enable this analysis. So I will right click on this, and then instead of this sign, I will put dot. So the syntax is there. Now dot OP I don't need. So I will just disable this by putting this sign, and this is disabled now. You see that? And now this got enabled. So let's hope that I am doing this analysis, and we'll see how the output will be plotted along with the input. So click run here. The waveform window appears, and let me clear all drawings. Now I want to plot V in. So on the schematic, you see the red probe highlights near the net. So I click here, and I have a linear increment or linear sweep of input voltage source. Now I want to plot V out. That is exactly following your output. So I would call it as a voltage follower. I will call as voltage level detector. I will call it as a voltage peak detectors, right? So many names can be given. How about I want to plot, because all the way the inputs are positive. So I want to plot the voltage drop across the diode. So I will see, right click on the waveform pan. I will say add trace. And here I will plot an expression which is voltage at node A and the voltage at the node V out. So difference voltage across the diode. So I will just click VA minus V out. So that expression I wanted to plot. So I'll see how it goes. And that's the red one. So it is like, let me just take it to add another plot, and here I will prefer to plot that. So what I see here, there is now some confusion, is because the voltages here are too high. And why is that the case? But input and outputs, the output is following the input. So let's do that in a moment. Let's figure that out and fix it. Okay, so the voltage drop across the diode is so high because apparently there is you are operating the op amp in an open loop mode. There is no negative feedback right here, getting your. But there is a when diode gets forward biased, there is a negative feedback actually. How can you say there is no negative feedback? So write in the comment section why you have such a large drop, let's say from 9.9 kV to 0 kV. So do that comment. Now, I would just prefer not to plot this, or I keep it like this, and let's figure that out again if we can do it. So here you see on the same pane, I right click and I would like to add the trace where I am actually trying to plot the current through the diode. So it goes from on the right axis, y-axis, it goes from minus 24 nanoampere up to minus 2 nanoampere. So when I'm sweeping, the voltage is negative from minus 5 to, let's say, onwards. I'm increasing the voltage from minus 5 onwards. The current is very low, minus 24 nanoamp, and then it starts increasing, approaching about 2 nanoampere when increases up to 5 or so. But if we look at the green and the blue curve in the bottom graph, output is very precisely following the input. How about we change the gain now? So gain is 1 mega. I actually this I do one thing. Uh, let's say I would set the gain to be 100 and we'll see how things happen. So I have decreased the gain to a significant level. And now you see you are V out and V in. So V in is your green curve, which is swept from minus 5 to 5, but your output is not tracking, not following the input. So it is constant all the way to, let's say 4 point something, and it is constant in the blue curve, right? Similarly, you can see, then in that case, red curves and this curve, this color, that the current through the diode is irrelevant. So that's the DC analysis. Let me just cancel, delete this trace, delete this pane only. And here is the input-output relationship. So it indicates the importance of having a very high gain of an amplifier. So I'm keeping it to be 10 e to the power 6. You can set as high as possible because this is a universal op amp. Now it is, you see now the green and the blue, they are on the same level right here, the same. How about doing the transient analysis of this amplifier? Right click, click advance, choose a sine wave source. Before that, let me see if we already have that arrangement on the screen. So let me see that. Do we have a transient source here? Not really. So what I'll do, I will right click this, click advance, click sine. DC offset can be anything, any value, but I've set to 0. Let's say I have 10 millivolt. I have a frequency of 1 e to the power for 10 kilohertz. Delay theta phi, I don't care. And then I have 10 cycles. So, okay, I have this sinusoidal source now that I am going to click it. And then I will enable this transient analysis right here. So I will right click. I will right click here and I will just select this analysis by putting a dot. As soon as I do that, I have to disable these two analysis. But even if I don't, and if I run, I will be asked to choose between the analysis. So now I am having a pure sine wave source at the input will run the analysis. See, it is saying there are multiple analysis defined for this circuit. Please select one to run. So I will select transient. So I'm running the analysis from time 0 up to 10 millisecond, and steps I don't define. So click OK. And now here I have the output of this waveform. Now what is wrong? Green is our input and blue is our output, and I don't see the output there. So anything that we are missing here, let's figure that out. Okay, so we now going to show you the transient analysis of it. So sinusoidal voltage source has been set up with a 5-volt peak with a frequency of 1 kilohertz. And we'll just run this analysis from 0 to 10 milliseconds. So I'll click run. And I have this waveform window where the green shows the sinusoidal input and the blue shows it is the output, that is the voltage across the capacitor. So you see, as soon as your input is about 2 volt or something, the output gets up to 5 volt and it stays there, uh, approaching the peak values of all sinusoidal peaks for the positive halves. And when the input is following, the output is still maintained. And unless the input comes again to the peak value. So it is tracking the peak value of here. So it is called as peak detector. So hope you enjoyed this video. For comments, write in the comment section, and do share with others, subscribe to the channel. Wish you happy learning.